Hi everybody and welcome to our 1.2 video. In this video we're going to be talking about domain and range. So your goal after watching this video will be able to represent domain and range of a variety of functions using a variety of different answers and formats. So before we jump in, just a heads up, Winnie is in my lap, so if you hear any noises or yawns or snoring in the background, he is currently sound asleep, so just a heads up on that one. But let's jump into our first definition here. So this is a little bit of a review, but to be fair, when we covered this last year in Algebra 1, it was in August, so it's been a full year since you've seen some of these things. So I thought the first page of your notes here would be a good idea to do a quick refresh of some of the things. So I'll go a little bit quickly, but if you need to slow down the video, you know how to do that in YouTube, and it should work just as well on Canvas as well. So don't be afraid to hit pause, ask questions, all those same types of things. So first word here, interval notation. And what we're going to define this is it is a way to represent a set of numbers using parentheses or brackets. So if you think about, for our examples here, something like if you have a line, let's start off on a number line. And we start off here, and we go to here. It would be super annoying to have to list all of these numbers out if I asked you what numbers are represented, because you'd have to say 2, 3, 4, 5. You'd have to also do like 2.1, 2.2, 2.3. Like you'd have to, it would take forever. It would take an infinite amount of time because there's so many decimals there. So that's where interval notation comes in for us, is it lets us write this quickly. A second note here, parentheses represent open dots. And when we see these on points, we're going to match parentheses with open dots. That's just a simple way of saying that if there's a number underneath it, it's not actually equal to that number. We use brackets, though, if we have shaded in dots. So what that's saying is, let's say this number here is 2. This top interval is not equal to 2, but if this number is 2, the bottom interval actually would have 2 in its range. It would be equal to 2. So just a really fancy way of saying if you see an open circle, use a parenthesis. If you see a closed circle, please use a bracket. So taking a look here, we have a closed circle, so we'll use a bracket. We have an open circle, we'll use a parenthesis, and then we just match it up to whatever's underneath it. So we have 2, and then we have 6. So that's the idea for interval notation. Again, quick review. Hopefully this rings a few bells. If not, like I said, no stress at all. We have the notes here. That's why we're doing the review. So a couple of things to review from this, though, and we'll go over some of these questions, and I'll even ask you to answer one on your own here, too. So the first one, all real numbers. That's just a really fancy way of saying everything. So if we're on the number line, the easiest way to think about intervals, honestly, is on a number line. And here's our number line. When we're saying all real numbers, we mean literally everything. So like we're starting here and we're ending here. So it goes on forever, forever, forever. So if you remember, if it goes on forever, 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 we just use infinity for that. So on the left side, it's negative infinity, and on the right side, it's positive infinity. And just a key thing to note, infinity does use parentheses because you never actually get there. Infinity just keeps going forever and forever. So our second one, we're looking at all numbers that are less than or equal to 2. So we can just write that as x is less than or equal to -2. And now we want to see this on a number line. And once we do that on the number line, it's going to help us to determine what is our interval notation. So here, less than or equal to -2. Okay, so I shade in my dot because it's equal to, and then it says less than. So less than means we're going down, down, down because it is less. So this arrow goes on forever, forever, forever. So parentheses, negative infinity. We have a shaded circle at -2, and because it is shaded in, we're going to use bracket. So that is our answer for this question. And if it wasn't clear, that was our answer for the question above. So I'm actually gonna hit the pause button on the video now, and I'm gonna ask you to jump in and do question C. Before that though, one quick thing that I do just want to note is if you have anything split up, so let's say for example, you have a set of numbers that, and I'll draw this off to the side here, looks something like this, and we have a gap. I'm sure some of you are remembering this. If we have a gap, we put in a U, or we call it a union. Then you would want to write 2 intervals around that. So you would do an interval for this one, and you would also do an interval for your second one, and then you would just join them with a U in the center. So you're like, why would I say this before pausing the video? Well, if you take a quick look, between 7 and 8, so between, to me, doesn't sound like it's including anything. And then secondly, it says larger or equal to 9. Okay, so there's 9. And we're just saying generally larger or equal. We have a gap here. So your answer, you're going to want to have the U for the union. So you'll have an interval that you'll put here. You'll type U, you'll put a second interval, and then you'll jump in there. So I'm going to hit the pause button on the video here. Put your answer into Canvas. We can see if you got this so far, and then we're going to keep going to our next definitions from here. All right, so hopefully you got that answer in. If you have any questions on it, just flag myself or Den what's down. We'll be right over to help. And our next word is domain. So domain is the set of values of the independent variable. An independent variable, that's generally most times x. So I like to think about this as it's from the wall to the wall. So your domain is your left right of your function. So just what is your x value? How far left does the graph go? How far right does it go? And it doesn't need to be any more complicated than that. If you can figure out left and right, you're good. Our next vocab word, you probably guess they go together, is range. And range is the set of values of the dependent variable. And this is typically, again, usually almost all the time, y. And the fancy way that I like to say this one is it's from the floor to the ceiling. How low, how high. And that's basically it. So if you got those two, if you can conceptualize and just remember left, right, up, down, you're going to be good. If you remember domain is x, range is y, you're in good shape. So that's going to be the review portion of what we're taking a look at for today. So now that we've done the review portion, we're going to jump into a little bit of practice and a little bit of the new stuff. So domain and range of finite sets. What finite means is it doesn't go on forever. There's just a fixed number of points. It is defined, and it's usually just a few. So some functions will only have a set number of elements. That just means there's a few. For example, our class is finite because there is a fixed number of students. So finite means there's, you can look around and count. And it doesn't go on forever. It's just however many people are around you in this room right now. If a function has a set number of elements and it has a fixed number of items in its domain and range. So this is a really fancy way of saying not interval notation because we list them. So if we take a look at our graph here, A and B, remember left x, right y, independent to dependent, however you want to remember that is fine. If we look at our domain, domain's just going to include everything that you see. So 3, 4, 5, 6, 7. That's the domain. If you look at range, I like to put these in order if I can. You just take a look at what you have there. So you have 1, 2, 3, 8, 9, 12. Just listing everything that you see. So What I'm going to do now is I'm again going to pause the video and going to have you submit what is your domain. List them out. And what is your range? Of your second example. So I'm specifically asking domain and range of this set of numbers. S just means set here. Hey, Winnie. So again, 3 points in your set. Well, you should have 3 points in your domain, 3 points in your range, just depending on what you're taking a look at there. All right, so again, pop in that answer, go from there. And now we're going to jump into our next type. So domain and range of infinite sets. So other functions can have infinite. Probably help if I didn't write in highlighter. Elements in the domain and range. For these, we will use our integral notation. To express the domain and range. So if we look at the graph below, and we're trying to find our domain and our range, I honestly look at this and I'm like, this doesn't look infinite. You know, it just kind of like there's 3 line segments, not a big deal. But if you think about it, like we said to start, it's impossible to name, even just what I have highlighted there, you'd have to name negative 2.999, negative 2.9998, negative 2.9997. It would take forever. Like literally it would be infinite in terms of how many small points are on that line. You can't list them all out because it includes all of them, all those little decimals. So that's where domain and range comes in. That's where we're going to be using integral notation. So when we start off here, this is the trick, and this is why I really try to emphasize floor to ceiling for range and wall to wall for domain. We really have to determine what each of these two things are. So if we're looking at this domain, how far to the left do we go? Well, it looks like we actually stop like right here. There's no arrow saying this line extends. And to the right, it's the same thing. There's no arrow saying that this line extends here. So it looks like we're kind of stuck at those points. And we want to make sure it's continuous. We don't want to miss anything. So if we are tracing from the left to the right, and we're trying to do this, so like we'll start at the left. We have an open hole and an open hole there. So that's something that we want to take a note of, because it looks like this line right here is not part of our domain because there's an open circle there. So it looks like there's a gap. And like we talked about before, we can put our U there. Sorry for when he's making noise in the background here. He's not a fan of domain. And then the second thing, if we keep going from left to right here, we're going to see another gap from here to here. So if we're tracing that domain and yellow is good and red is bad, we have that gap from like 3 to 4 to 5 to 6 is not included in our domain. But if we jump back to our yellow, we're going to see we keep going. So we're just looking at x values here. We don't care about up and down at all. We just care about left to right. So looking at this domain, looks like you can just guesstimate this here. It looks like, I don't know, maybe we're starting off at like negative 5.5, and then we get to negative 3, and there's a gap there. So we have to put our parentheses, put our U for our gap, start up again at negative 3, and we make it all the way to positive 3 this time with a nice little bracket. And then we have our second little red window gap there. So another union, and then we'll start again at 6. And we'll finish 11, 12, 13. I think it's like 14 and a half. And that would be our domain. So left to right, we're tracing it. We see a couple of gaps, but basically everything that we wrote down there is our domain. And it seems like a lot, but it's basically just putting a couple of questions together at the same time. So we're looking at 3 lines here that are kind of on the same graph. So if we're taking a look, it kind of makes sense that we have 3 intervals. So now we're going to want to do the exact same thing, except this time we're going to go from bottom to top. So let me clean this page off a little bit. And let's take a peek from how far down we start at, which is like right here. And if we trace this over, it actually keeps going up, so that's good. So if we're tracing on our y-axis here, it looks like we get this entire range, and then we have a gap. There's nothing up and down right here, and then we start back again from here to here. So our range actually looks like there's less gaps. There's only going to be one union. So if we start off at like negative 8.1 maybe, again, just guesstimating here, I think this is like our lowest point on our up and down range. We make it all the way to 1, positive 1, and it's closed circle, so we put that bracket. We have a gap for the union, nice and open again at 2, and then we have a closed nice interval there at 4. So that would be our range. This is about one of the more challenging types of examples you'll see because, again, there's 3 lines. Typically, you'll just see like 2, but putting 3 together does make it a little bit more challenging. But thing to remember here, domain is telling us left to right, and range is going to tell us what goes up and what goes down. All right, last thing for today, restricted domains of functions. So this one, we're not looking at things anymore. We're going to be doing basically what's related to solving here. So for restricted domains, there are 3 functions specifically of the family that we've looked at this week that are not always real numbers. And what that means is when we see these functions, it's a big red flag. We know we need to do some evaluating to make sure. So we have the square root, index of 2 there. So square roots, we have our reciprocal. So this is typically when you see like x on the bottom, something like that. And we also have our logarithmic. So basically any times you see here, it's like you see log written down, like literally if you scroll down here, if you see log written down. So for our square root functions, the domain is always values that make it non-negative. So it can be equal to 0, it just can't be anything that's negative. And we always want to make it positive or 0. So those are the 2 options. So positive or 0, anything other than that is not included in our domain. Reciprocal function, always values that make the denominator not equal to 0. So if you ever see a 0 on the bottom of a function, that's bad, not real number, so not our domain. Logarithmic function is always values that make it have positive values. And I want to be specific here. It does need to be greater than 0, so we can't have anything that's actually equal to 0 for a log. It can be 0.0001, but it can't actually be 0, so we have to make sure of that. So for our examples here, we're going to take a look at the domain, and we're basically trying to see what does the domain not equal. So if we ever see a square root, we have to make sure that it is not a negative value. So what we're trying to do here is set this x plus 3, and it has to be greater than or equal to 0. It can't be anything that's negative. So from here, we can just basically solve this inequality. So move 3 over, x is greater than or equal to negative 3. So any value for x that is bigger than negative 3 is going to give that root a value that is non-negative. So what we can do for that, take a look at this on our number line, greater than or equal to negative 3. Sorry for Winnie's noises, he's definitely engaged here. I think he's trying to learn. So we start off on the left side at negative 3, and it goes on forever, 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 all the way over to infinity. So that's what we're going to look at for our domain on our first one. For our second one, we have our variable in the denominator. That's going to be our reciprocal function. We want to make sure that the denominator is not equal to 0. So we can take that denominator and make sure that it's not equal to 0. So we just solve this so that it's not equal to 0. So add 4 to both sides, and we get x squared is not equal to positive 4. And then what we can do from here And there's a couple different ways to solve this, so I want to be clear about that. So you could have factored this if you wanted to. You could make that a polynomial and break it down into the box method. You can also take the root of both sides, and you'll get x is not equal to, and this is the thing, it's not just 2, it's 2 and negative 2. So the square root of 4 has a both positive and a negative value here because it's that. So x does not equal 2 and x does not equal negative 2. So our domain is all real numbers not equal to 2 and negative 2. So writing that as an interval, you can do that. It's honestly a little bit easier to just write it as, wow, that knocked all of the work out, that's great. Just easier to write it as x is not equal to 2 and x is not equal to negative 2. So those are two things that you want to note for that second one. So for our log here, what we're going to want to do is take the inside of our log, and if we look back at our log notes, it's going to say that, again, this is one that has values that are positive. So 2x plus 1 here, it has to be bigger than 0. So you're going to want to go through and solve that and write that answer. And we're going to end there for today because I don't want to have this one go on for too much time. But our last question would just be taking a look at the top and the bottom. We would have two things to solve. We'd have to solve a square root, and we would have to make sure that our reciprocal function does not equal 0 on the bottom. So those are the two pieces that you're going to want to take a look at here. So for our last piece, what I'm going to do is I'm going to ask you to just input an answer for this function for the domain. So what is the domain of the log of 2x plus 1? All right, thanks for watching. I know that there's a lot in this video. Welcome to pre-calc. If you got questions, let me or Dunwitz know. We are here to help you every step of the way.